This recording shows you how to work with this Gravitation Applet. First, go there from within the lab sheet, so I'm going to hit Control, click on there, and I'm going to get it. There, that's what it opens. Now you click on Run Now, and there's the applet. Okay, let's see what it says we're supposed to do. As I said, I'm going to do just a couple of 3 examples. I don't think I'll be able to fit everything in here. There we go. Okay. I'll actually leave this off the screen here so I can read it myself. Alright. It says select the preset Sun and Planet. So I'm going to do that. Now it says change the y velocity of body 2 from 120 to 140. So here's body 2 and I'm going to change it to 140. What is the shape of the planet's orbit? Of course, at this point I'm going to start it. And there we go. There's one full orbit. Okay, and now it asks, what is the shape of this planet's orbit? Well, this is an ellipse. Which law says it would be of such a shape? Kepler's first law. Why does the Sun describe an orbit as well? Well, because the two attract each other gravitationally. And so it's not just that one is going to orbit around the other, but the second one is also going to orbit around the first one. So both describe an orbit because of the gravitational attraction between the two. Why is the Sun's orbit smaller? Well, because the Sun has a much higher mass than that of the pink Earth in this case. And you can see that the mass is here 200 versus 10. And because of the smaller mass and Newton's second law, the acceleration is much less on the Sun than it is on the pink planet, and so the resulting orbit is much smaller. Okay, let's do the second one here. Sun, planet, and moon. It says let it run the way it is. What kind of shape does the moon's orbit around the Sun seem to have? Well, it could be kind of described as a flower-shaped orbit. Which of the other two bodies exerts a gravitational force on the moon? Well, since we know the gravitational law, both of them, both the Earth as well as the Sun, exert a gravitational force on the moon, and in turn the moon, of course, exerts a gravitational force on both the Sun and the Earth. That's Newton's third law as well as the gravitational law. Now turn off the show traces. So I'm going to do that. What kind of shape does the moon's orbit around Earth have? Well, looks like either a circle or an ellipse. Okay, I'm going to do one more example, which is the last one, the one with the ellipses. Second to the last one. It says check the show traces, show grid, and tape measure. Show traces, show grid, tape measure. Let it run the way it is. You now see 3 important astronomical laws at work. Name them and write them down in short form. Well, we see Kepler's first law, which is planets orbit on an ellipse, or any kind of body orbits on an ellipse. We see Kepler's second law. For example, look at the green one. The furthest it's away, the slowest it is, and the closer it gets, the faster it gets. And we see Kepler's third law, which says that the distance and the period of a planet are kind of proportional. The larger the orbit of a planet is, the longer it will take it to orbit respectively, you have the p squared over a cubed or a cubed over p squared relationship. Okay, now it says reset and change the slide bar's accuracy to 1 unit. So put this at 1 unit here. Stop every time a body completes the one orbit, and I'm only going to do it for the pink one here. So I'm going to start it and then stop it when it's done, right there. Okay, I cannot do it any more accurate. I'm measuring time of 2.3. It says measure the horizontal width of each orbit and divide by 2. That yields the semi-major axis of each orbit, which is the average distance from the Sun to each body. So I'm going to measure it here, right there to there. Okay, that reads 141, and I'm supposed to divide by 2, so I'm going to come up with 70.5. And then the period comes out to 2.3, because it's only two significant figures anyway. I could just say that my distance is 71. So my average distance is 71. My period is 2.3. By the way, if I go just a little bit further, right there, see, I cannot even click that accurately, and 2.3 is just short of one orbit. 2.4 is actually quite a bit further, so 2.3 is a good number for the period. So that's what I'm going to plug in here, 2.3. These are kind of arbitrary chosen units by the applet itself, so they don't have any seconds or something attached to it. And I said this one here is 70. And now on the calculator on the side, I'm going to do 71 cubed divide by 2.3 squared. So it's 71 cubed divide by 2.3 squared. Enter. That's around at 68,000. By the way, had I used the 70.5 earlier, I guess it's going to be a little bit different. 2.3 squared. And that would be around at 66,000. You would have to keep in mind that you only have two significant figures here. So 68,000, 66,000, there's already a little bit of an error in there. I'm going to plug that in here, so 68,000. And what would you have to expect for the blue and the green one? Well, basically the same, because that's what Kepler's third law says. And with that, I conclude this introduction to how to work with the applet on gravitation.